Okay, good morning, Gators. Um, Today I wanted to talk a little bit about chemical reactions. Let's go ahead and share the screen here. And let's go ahead and present. Right, so chemical reactions, they're all around us. So here we have them running the bulls in Pamplona or whatever it is in Spain. And they're running and they're going all sorts of crazy things. And to do that, to get the energy, they have to carry out cell respiration and convert oxygen and glucose into ATP and carbon dioxide and water. And that's a chemical reaction. When food decomposes, so if you look in the fridge and there's all this gross stuff that doesn't look anything like the food that started, that happened by the compounds changing as a result of decomposition. When metal rusts, that would be an example of chemical reactions, or fires, or when you cook, like an egg cooking or something like that. So much more all around us. Those would all be examples of chemical reactions. Now, in chemistry, when we write chemical reactions, we put the the reactants on the left side. So the reactants are the things that go into the reaction. And then the reaction happens, and then you get products are what's made as a result of the reaction. And to indicate the reaction, you put a little arrow. So a generalized format for this would be reactant 1 plus reactant 2. The arrow means reacts to yield, product 1 plus product. You can also put states of matter in there. So S indicates a solid, L a liquid, and G a gas. And we also have something called aqueous, and that's dissolved. So if you dissolve salt in water, you'd have like an Na plus ion, and that would be aqueous. Now, chemical reactions can be expressed a few different ways. One way is with a word equation, and that verbally describes what happens. So, for example, oxygen and hydrogen gases combine to make liquid water. Now, what we can do is convert this into more of a formula approach. And to do that, I have this fancy new formula, this guy. And we can say, well, oxygen and hydrogen are both Brinkelhoff gases. So we can say O2, because there's two of them. They form a binary compound gas there, gas, plus H2 gas. Combined to make, that's the reaction, so we put an arrow, and then liquid water. So water is H2O, liquid is indicated with an L. So that would be a unbalanced. Notice they aren't balanced yet, but that would be the symbology to represent this word equation. Now, a skeleton equation, again, just shows the it just shows the elements that are not balanced. So you don't have the same number of atoms on each side, but it does show the elements that are there. So to make a skeleton equation from this word equation, you kind of would do the same process. So we have carbon monoxide, which would be CO, so carbon monoxide, that's a gas, plus oxygen gas, again Brinkelhoff is O2, reacts to yield then carbon dioxide, so C dioxide is two oxygens gas. So carbon monoxide gas plus oxygen gas reacts to yield carbon dioxide gas. This would be a skeleton, unbalanced equation of this word reaction. Another one is shown here. So potassium chlorate. So we have K is potassium. Now we have to do a little bit of thinking here, because chlorate is, K is a plus ion. This is an ionic compound. Chlorate is ClO3, and it's just minus. So those are equal and opposite, so they're balanced. So K, ClO3, reacts to yield now. Potassium chloride, this is KCl, plus minus. KCl plus oxygen gas. So this is and this one, this one. So that would be your chemical skeleton equation for this reaction. Okay, and I'm going to make a plus and minus 1 charge. Now, generally in chemistry, when you do a chemical reaction, you want to have the same amount of stuff on both sides. So the same number of oxygens on both sides, the same number of nitrogens on both sides, because there's conservation of mass, and you can't just create oxygen out of nothing. Now, to do that, it's useful to take what's known as an atom inventory and basically count how many atoms of each element are on each side of the equation. If the number is the same, then you're all good and the equation is balanced. But if it's not, then you have to use coefficients which tell how many of each molecule or compound you have. It's the number in the front of the molecule, not the subscript. And you use those coefficients to balance the reaction. In some cases, we're doing chemical reactions with carbon, hydrogen, and oxygen. Do oxygen last in that situation? It just makes the balance easier. So, the general format for writing balanced equations for Moivre equations is write the reactants on the left side, connect with a plus sign. Now remember, subscripts are written here. So they're formed prior to balancing. So something like calcium, I don't know, calcium chloride would be Ca. Since Ca is 2 plus, you need 2 chlorines, so CaCl2. That would be a subscript. Then use an arrow to show the direction of the reaction, and then write products on the right side. Do an atom inventory of reactants and products, and then change the coefficients to make the number of moles or atoms on the side of the equation equal, on both sides equal for all the elements. We haven't talked about moles yet, but it works fine. Talk about it in terms of atoms. Then make sure that your coefficients are written at the lowest possible ratio. If you get like 2, 2, 4, that would simplify to 1, 1, 2. Make sure to check your work, and then again, once again, never, ever, ever change subscripts to balance the equation. So a couple examples here. One would be this: carbon disulfide reacts with oxygen gas, producing carbon dioxide and sulfur dioxide gas. For carbon disulfide, that's going to be CS2 plus oxygen gas, O2, produces carbon dioxide, CO2, and sulfur dioxide, SO2. And I think I have that written out there. Yeah. So it's not balanced as written. So then we have to do an atom inventory and then balance. So with that, we have on this side, we have carbon, we have sulfur, and we have oxygen. Okay, carbon looks like we have 1, sulfur looks like we have 2, and oxygen looks like we have 2. On this side, we have carbon, let's keep the same order, sulfur, and oxygen. Carbon, again, we have 1. Sulfur, we only have 1 there. And then oxygen, it's a little tricky. There's 2 here, there's 2 there, so that's 4. Okay. Now, notice there's 2 sulfurs here, 1 sulfur there. And again, always try to do oxygen last. So 2 here, 1 there. So one thing we could potentially do is put a 2 in the front. And again, it has to be the coefficient. But a little button there. Put a 2 there. And that would make then 2 sulfurs here. So that makes this into a 2. Okay, but it also makes oxygen into 4 here, plus 2 is then 6. Okay, so now we have 1, 2, and 6. Well, the 1s match, the 2s match, but this is 2 and 6. Well, conveniently, we can now put like a 3 there, and 3 times 2 is 6. So this becomes 6, and we have 1, 2, 6, 1, 2, 6. It's balanced here. So I think I printed that there. 6 here. Okay. Another example could be this one, where we have iron 3 chloride. Iron 3 is a +3 charge, which means we need 3 chlorines to react. So FeCl3 plus sodium hydroxide, NaOH, plus 1 minus 1, reacts to yield solid iron 3 hydroxide, so Fe, that's a 3 plus charge, so we need 3 OHs, and sodium chloride, NaCl, plus 1 minus 1. So when we write the equation now, we get FeCl3 aqueous plus NaOH aqueous reacts to yield FeOH3 solid plus NaCl aqueous. Notice though that this is not balanced. So now we go back and we do the balancing. So you can write your atom inventory. FeCl, NaOH. Well, for iron, there's 1. For chlorine, though, we look at that, there's 3. For sodium, there's 1. For oxygen, 1. Hydrogen, 1. Now, those were the reactants. Now, arrow, that's the reaction. Here's the products. Let's keep the same order here. So irons, it looks like there's 1. For chlorine, chlorine's over there. There's only 1. Next one is sodium. And sodium, it looks like there's 1. What's next? Oxygen. Oxygen, there's 3 O's. And finally, hydrogen is 3 H's. So you'll see here we have a couple things that aren't the same. One is we have 3 Cl's here and only 1 Cl there. So one thing we might want to do is put a 3 here. Okay, now that is going to do a few things. One is it's going to make 3 NAs here, and it's also going to make 3 Cls. So now our Cls match, but now our NAs don't match. Okay, our O doesn't match, our H doesn't match. But since we have 3 NAs and only 1 Na here on the reactants, we can put a 3 there. Okay, that's going to make 3 reactant NAs. There's a 3. 3 reactant O's and 3 reactant H's. So now you'll see that all of the elements, it's the same amount of stuff on both sides. So conservation of mass is in place and we're all good. And I think that one wasn't balanced. I think I wrote out, here is the balance, just a little bit later. Okay, so that does conclude a little bit of description about chemical reactions and balancing chemical reactions. So with that,